Good morning. Morning, guys.
Good morning.
Right. So, how is everything going? Fine? Okay. Uh, so does anybody have any questions about exam review questions? Those 21 or 22 questions at the back of the book. No?
No.
Okay. Okay, guys, I have a request. Would it be possible? There's no pressure, but would it be possible that we take the first quiz on the 21st rather than the 22nd? You can think about it, but just let me know.
Would we have class after?
What do you mean after?
Like take the quiz I know in AMP sometimes we would like learn stuff after.
But okay, at least we're going to go over the quiz.
But like that's probably it.
Let's see how long it. But like, okay, if you need to leave early, you can always do that, Maria.
Okay, yeah. I would have to leave like after we review the quiz.
That should be fine. That should not be an issue there. Anybody has any issues? Okay, no pressure. If you can't, then just let me know. Okay, via email. But please try to do so before the end of the day. Okay. Okay, guys. So are you guys done ready for are you guys ready for the next chapter now?
Yep.
Good. So chapter number 2. Okay, guys, now in this chapter here, I may be jumping a little bit back and forth between the first 3 pages. Okay. So okay, let's see. Good. So first, that's okay. This is going to be about sound. Okay. Now the first thing that we can see about sound is that, okay, yes, sound is a form of energy. Okay. sound is going to be as okay a form of energy. Now, one thing that you guys will as okay need to know about energy is, and we'll talk more, come across that in further details later on, but just for now is that okay, yes, because it's okay that energy can as okay yes change its form. Yeah, okay. So yes, okay. What first yes, okay, or what your system, ultrasound system is going to produce as sound didn't start as sound. Okay. Just like okay, yes, the light that is on right here is okay in the background. What the hell? Okay. Yes. Okay. Didn't start its journey as light. It was electricity. Before electricity, it was some other source that okay as a combines okay at a grid station. Gas, oil, atomic, whatsoever, that produced electricity. Clear? Okay. So these are different forms of energy. So one thing that okay, yes, energies may have the tendency of doing is changing their form. Clear? Okay. Okay. But there needs to be as okay, you can say as okay, some sort of tool or process that is going to as okay enable that change for occur. Okay. Okay. So our sound that is okay that our ultrasound machine is going to be producing didn't start from the very beginning as sound. First, it was electricity. That electricity is again just going to be produced, converted into sound. How that happens, that's something that we'll talk about in a later chapter. Okay, but we can say that okay, sound is a form of energy. Okay, now when we talk about yes, okay, types of energy, what you can say is okay. So the category of the type of energy that okay, sound energy is going to fall under is going to be yes, okay, what we will call. So sound is going to be yes, okay, what form of energy? What we call mechanical energy. And why is that? Why do we call it a mechanical energy? Or why is it going to be as okay, a type of mechanical energy? Mainly because what actually is okay causes the sound wave or sound to travel is going to be yes, okay, what we can call particles. Okay, that actually is okay will move what we can say is okay back and forth. Okay, did that make sense? So mainly because okay, sound energy is going to be produced as a result of moving particles, or we can make it okay to be more specific, this is particles in a medium. Right, okay. That's why it's going to be referred to as being a mechanical energy.
So mechanical energy is particles that move in a medium?
Now, we can say it's okay, a type of energy in which there has to be particles that will be moving.
Okay.
Did that make sense?
No.
Huh?
No, to be honest, no.
Okay. There got to be particles. Clear? Okay, there got to be particles for yes, okay, sound to be able to travel. Okay.
Okay.
Okay. Now, mainly because, okay, these particles here, you can say, okay, we can take this one here. It's not going to be stationary. It's going to be moving, or we can say, okay, back and forth. So is this one here going to be moving back and forth. So is this one here going to be moving back and forth. Did that make sense?
Yeah.
Okay. So you can mainly say, okay, this movement of the particle, that's going to be, okay, some sort of mechanical activity that actually is, okay, causes or produces just, okay, a type of energy. Did that make sense?
Yeah.
Okay. Okay. So one thing that you will have is, okay, we'll take away from now is this is that, okay, yes, one thing that we need for sound is going to be what we'll call a medium. Okay. Generally speaking, all sounds will need a medium. Okay. And what is it that medium is going to have? Yes, okay. It will need particles. Particles or substances or whatsoever. Did that make sense? Now, guys, when I am talking, even yes, okay, we were sitting in the same room, let's say. We can say, yes, okay, the ear or the room between my mouth and your ears, that's going to be the medium. Clear? Okay. For regular, that's okay, audible sounds that you are going to be able to hear. Okay. So you can mainly say, okay, what is going to be the medium? That's going to be as okay, the substance or the space or whatsoever through which the sound will travel. In general terms, we will call that a medium. So all sounds needs a medium to be able to travel in. Did you guys get that? Okay. Another thing that we need for a sound, or let me put it this way. Another thing that we need for a sound is going to be, it's okay, what is going to be called a source. Now, if you just take, yes, okay, an example of what's happening right now. Right now, yes, okay, there's a person sitting in his living room and talking. Did that make sense? So whosoever is talking, whosoever is producing a sound, or whatsoever is producing the sound, is going to be referred to as the source. Source, we can say, okay, we can be more specific, we can say, it's okay, the source of sound. Okay, but what do we mean by the source of sound? Mainly, it's okay, the person, the object, the thing, so and so that produces the sound. So whoever right now, yes, okay, if I'm sitting here and talking, what it is that I am, I'm the source. Okay, a car passing on the street. That car is going to be, yes, okay, well, okay. More likely, it's going to, yes, okay, transport a person or persons. But okay, what it also may be doing is producing sound. So that's going to be, yes, okay, a source of sound as well, right? Okay. So without a source, yes, okay, you didn't have anything that was producing the sound. I can be sitting here. Well, okay, I'm sitting here. But in this break, was I a source of sound? No, because I didn't produce a sound, right? Clear? Okay. So once, yes, okay, I produce a sound, well, we can mainly say, yes, okay, that sound produced by the source, yes, okay, most likely, yes, okay, will now have to, or we can say, yes, okay, it will be traveling through the medium. Or what's going to be the medium? Yes, okay, in this case, yes, okay, I mean, like I say, it's okay, the space between, yes, okay, the source, and let's say, yes, okay, the receiving end. Hopefully right now, yes, okay, the receiving ends would be, yes, okay, your ears. Clear? Okay. But even if there wasn't anything, yes, okay, receiving. Okay. I could be talking to myself. Nobody's listening to it. Okay. But what we still would have is a source producing a sound, and okay, as a medium through which that sound would be traveling. Did you guys get that? So that is in general. That's when we talk in general terms. So what do we need for a sound? We need a source. Clear? Okay. And for that sound to travel, well, okay, yes, there would need to be a medium.
So you
Okay.
don't technically need a receiver.
No, I could be
Okay.
speaking to an empty audience or to a room with empty tables and chairs. Or I could be speaking to, yes, okay, the man in the mirror. Did that make sense?
Yep, thanks.
Okay. Now, my idea, you could be sitting in that room, nobody around you, not on Zoom, not on Boom, not on Twitter, not on whatsoever. Okay. Or TikTok or whatever you call all those things. And you can still be talking. You'll be the source. Clear? Okay. You can still, yes, okay, spread the message on the medium. But that's okay. If nobody views your video, for instance, that's okay. That's not going to mean that, okay, yes, you didn't produce a sound and that sound didn't travel in the medium. Does that make sense?
Yes.
Clear? Okay. So the main two things that we would need for a sound to be produced and travel, or okay, you can say travel is, well, okay, first of all, there needs to be a source. Without a source, well, okay, no sound is produced. When no sound is produced, forget about it traveling, right? If I just say, yes, okay, I could be a source of sound, but I chose not to produce sound, right? Okay. But as okay, once I produce sound, well, okay, yes, that's when I become okay as an actual source of sound. And then, well, okay, for that sound to as okay, you can say travel, it would need a medium. Did I make myself clear on that? Any questions? Any questions? So, in ultrasound, this was just general talking as okay, regular, okay, audible sounds that you could hear. Okay, sound of the teacher, sound of okay, as somebody is okay, playing the music in the background. Okay, yes, a dog barking, so on, so on, so on, so on, so whatsoever. Those are all sounds. Okay, but had there not been a medium through which, yes, okay, those sounds could travel, we would probably not have been able to hear them, even if they were produced. Is that clear? Okay, so source and medium. Mainly as okay, just going to be as okay to generalize terms that we can use to yes, okay, what produces the sound and what, or as okay, through which the sound will travel. Clear? Okay. In ultrasound, or as okay, sonography, as you may call it, your source is going to be as okay, the transducer. Yeah, okay. It's going to be the transducer. You may from time to time hear me that I may use the word probe. That may just be as okay, a slip of tongue. Okay, but that's okay. What it practically is okay, just going to mean is that's okay, your transducer. Okay, so well, okay, yes, we will have okay as an account of yes, okay, the transducer in chapter 8, and mainly yes, okay, talk a bit about yes, okay, how the transducer actually was able to yes, okay, change electrical energy into sound. Okay, but the source of your ultrasound, or you can say, okay, in this case, the source of sound is going to be the transducer. Okay. Now, some of you will say, okay, what is going to be the transducer? Or what do you mean by the transducer? Well, that's actually, that's okay, that joystick-like thing that they may be, as okay, applying onto your belly, arms, legs, neck, wherever, chest, whichever area that they are scanning. Okay, so that's what we call the transducer. So that is actually, yes, okay, where your sound is going to be produced. Is that clear? To begin with, yes, okay, we will not refer to as the transducer, we will just refer to that as the source. In the next chapter, pretty much, that's okay, what we were talking about is okay, yes, different parameters, and it's going to be, yes, okay, a question. Is this a parameter that is produced or determined by the source? Or is it going to be a parameter that's going to be determined by the medium? So your source will be the transducer. The medium, now that's okay. When I produce sound here, that's okay. Because that's okay, the space between, that's okay, my lips, and okay, yes, the microphone in my system here will be the source. Oh, sorry, the medium. Even as okay, you can say, okay, the electrical or digital medium of the internet, of Zoom, is going to just okay ensure that okay, yes, whatever sound I produce is going to hopefully reach to your ears. So that way, as yes, okay, different medias, right? Okay, okay. But as I said, for a sound to be able to travel, yes, okay, you will need a certain kind of medium. Okay. Now that was generally speaking. That was generally speaking. In ultrasound, what is going to be our medium?
The skin or the organs?
Your tissues. Clear? Okay. That's going to be your medium. But until and unless that's okay, we haven't got to that point, we mainly will just say that okay, yes. Medium, well, okay, that's going to be that's okay. We can say it's okay. The substance through which that's okay, the sound waves will travel. But in ultrasound, that's okay. What's going to be our medium? your tissues. Is that clear? So whether we say so what do we need for sound? Which of course is okay, was and energy. Or we can say it's okay, a form of energy. Yeah, okay. For sound, yes, okay. One thing that was going to be needed was going to be yes, okay, a source.
Mike, what does that say after sound?
Energy.
Okay.
We already said that sound is a form of energy, right?
Yeah.
Okay. So what was it that we needed? Well, that's okay. We needed a source. And okay, yes, we will need a medium. Yeah, okay. In ultrasound, well, okay, yes, our source is going to be as okay, what we will call the transducer. In ultrasound, yes, okay, our medium is going to be the tissues. Yeah, okay. If you don't like the word tissue, well, okay, you can always say yes, okay. Organs, whatsoever, so that doesn't matter. Okay. But what we just said, or I just said earlier, was that okay, yes, this medium here is okay. What is that going to be made up of? Different particles. Yeah, okay, and it's going to be as okay, these particles that's going to be moving back and forth like this. Okay. And due to yes, okay, this back and forth motion of the particles, that's why as okay, sound was a mechanical form of energy. Now, guys, as sound need a medium, and that medium, and especially as okay for sound, as okay needs particles, and those particles will be moving. Okay, those particles will be moving. Okay, now medium, my guys, actually it can be in three forms. Or we can actually have okay, three forms of medium. One form is going to be solid. The other form is liquid. And the third form is gas. Or we can say as okay, a medium can be as okay, can have three natures. So there are three major natures of a medium. Just look around you. Well, okay, yes, the most things that are visible around you right now are solids, right? Right? Unless, okay, you are as okay, floating around in a swimming pool on a floaty in the sun, wearing your sunglasses, as okay, and a glass of or shower. Clear? Okay. But that's okay. And most of the objects or things that you'll see around you are solids. Liquids will be as okay, any liquid. Milk, water, juice. If we talk about is okay, a liquid tissue, that will be blood. Or a liquid medium, that's okay. Urine, for instance. It doesn't have to be as okay a physical tissue, it's just a medium. So a form of medium, right? Okay. Okay. And then you have gases. Now gases mainly as okay going to be air. Okay. Did you guys get that? Okay. So three different forms of a medium: solids, liquids, and gases. Okay. And what are these three forms of medium here have in common? What these three forms of media here have in common is that they're all going to be made up of particles. Okay. The main difference between them is okay, as why is something solid, why is something liquid, and why is something is okay in the form of a gas. It's all dependent upon yes, okay, how densely packed or close to one another the particles are that makes up that medium. Did that make any sense? Or you can actually assess, okay, say the density of that medium. But let's not get into that yet. Okay. But one thing that, okay, as all these three media here in common was that they had particles in them. Did you guys get that? Okay. So these will be as okay, three forms of medium through which yes, okay, sound will be able to travel because they got particles, which were going to be moving back and forth and cause the sound wave to travel. Did you guys get that? Anybody who is lost? So far, everything is clear?
Yeah.
Okay, if it's not, please, guys, please let me know. Okay, I don't mind explaining it again. Okay, so now just one little yes, okay, takeaway point here is that in solids, there's going to be a remaining, it's okay, we'll say that okay, as the sound is going to be travel at a faster speed. Whereas in liquids, you can say it's okay at a slow speed. Whereas in gases, that's going to be as okay the type of medium in which as okay the sound is going to be traveling at the slowest speed. Okay. Yeah. Okay. So just take this one here as okay with you, because that's going to become yes okay relevant in the next chapter. And this is general physics, if you want to put it. Okay. General physics of sound. So it may sound crazy, but it's okay. A sound is going to be as okay traveling faster through a rock. Right, okay, than a gas chamber. Okay. Right now, it's okay saying you it's okay, that's okay. What we have between us is air. But it's okay, the sound had reached you faster had you been it's okay submerged in water. But what was common in all these three forms here of medium is that they are made up of particles. Yeah, okay. There's a form of medium where there is no particles. And that's what you call a vacuum. That's what you call a vacuum. And that mainly as okay will mean that okay as in a medium which is a vacuum. Well, okay, what do we have in a vacuum? That's going to be as okay a medium with no particles. And since that's okay, there are no particles, that will mainly mean that okay, yes, well, okay, there will be no particles. So that's okay, because that's okay, which would move or which could move back and forth. And that mainly causes that okay, as a vacuum cannot produce as okay mechanical energy. So which actually is okay makes it impossible for sound to travel through a vacuum. Okay, so a vacuum is going to be as okay a complete empty space. Okay, which is so empty that it doesn't even have particles in it. Okay, and there was meaning yes, okay, going to be as okay, this movement of these particles, yes, okay, back and forth, that cause the sound wave to be able to travel faster, slower, or even yes, okay, slowest. But in a vacuum, there is no particles, so there's going to be a medium in which the sound wave can't travel. Did you guys get that?
Yep.
Okay. So mainly because that's okay. In a vacuum space, there is no particles. Okay, not even air. So that's okay. Air is going to be as okay sucked out of a space. Then it becomes a vacuum. Okay. But that mainly cause that okay, yes, you will not have yes, okay, what is going to be necessary for the sound waves to be able to travel. okay, which needed as a medium with particles. Those particles could be close to one another. We will call that medium a solid. Those particles could be slightly farther away from one another, and that would be a liquid. Or they could even be farther away from one another, and we'll call that a gas. Okay. And guys, that's okay. There's one medium or there's one substance that we have easy access to, which actually is can get into all three forms. That would be water. Now, hopefully it's okay when you turn on the tap or hose or whatever you call it. That's okay. The form in which you will see the water coming out and is going to be liquid. But you can put that water in a container or whatsoever, and it's okay, place that in the freezer. Sooner or later, it's okay, the water is going to turn into a solid form that you call ice. Is that clear? If you want to, yes, okay, you can put that ice in a pot and place that on a stove and melt it. First, it's going to turn back into liquid, and sooner or later, yes, okay, it will turn into gas. Okay. Now, the reason that ultimately, yes, okay, you see what you can call the mist or vapors is mainly because, okay, that gas decondenses or condenses back into liquid. Okay, because it cools down as it leaves the pot. But if the room is warm, well, okay, yes, it will not, yes, okay, cool down to become, yes, okay, what you can call vapors and so on. So, okay. So that's pretty much also just okay what happens when it becomes foggy out there. That you can say it's okay, a sudden change of okay, yes, temperature of vapors, which is gas, gets condensed or cooled down. And it turns into it's okay, what you call fog, mist, so on, so on, so. Okay. That's why you don't have fog in summer. But is water going to evaporate? Yes, it can. Have you ever wondered, yes, okay, why is that you may see, yes, okay, smoke from the streets after a couple of days of just okay, severe heat and okay, as there was a rain. What it means is okay, that rain we have water which is evaporating. But why do you see the mist? Because okay, what the rain does, it cools down the air. Otherwise, it's okay, that was just going to be as okay in the form of gas, which is invisible. Did that make any sense? Okay. But yes, okay, our takeaway line is, well, okay, yes, sound travel fastest in solids, slower in liquids, and slowest in gas. Clear? Okay. And in vacuum, well, okay, it will not be able to travel. Why? Because that vacuum didn't have the particles or I mean is okay, just a medium with no particles. And it was actually just okay going to be okay that back and forth motion of those particles that will cause the sound wave to travel. Did you guys get any of the words that came out of my mouth?
Yep.
Are we having a big vacuum between me and you guys? Okay. Okay, now guys, if you look at the bottom of your page, or the first page of chapter 2, there's something that says sound wave or sound travels in a straight line, right? Sound travels in a straight line. Please underline that one. Okay. Because, okay, one of our things that we as okay may have to be dealing is okay later on in the chapter is okay as how to change that. Or I say okay, change not change it as okay, but use this to our benefit. Okay. The following line says sound waves are longitudinal waves, right? You guys wonder why it's okay the word longitudinal is written in bold and straight lines was written in bold? Why? Why would you write something in bold?
It's important.
Okay. But what's going to be the point of us writing it in bold then? These guys, it more likely will catch the eye, right? Okay. You open a book on a page, that's okay. Probably that's okay. Oh, okay. Hopefully you should be able to read all the other text as well. But okay, what immediately will catch your eye is going to be as okay, what is written in bold. So what do we have written in bold on the pages before? Media and transducers or source, right? Okay. Energy. Because okay, what we may say that okay, as what is that sound is going to be? Sound is going to be as okay, traveling in the form of waves. Okay. What kind of waves? Longitudinal waves. So what do we mean by it's okay being a longitudinal wave? No idea?
Isn't it from like top to bottom?
Okay. From top to bottom. A line that goes, okay. A line that goes from top to bottom, my dear, is, what will you call that? If I draw a line from top to bottom, or a line like this, let me do it on the board. Yes, guys. What we will call this, or what would you call this line here?
Vertical,
Pardon me, dear?
a vertical line?
Is vertical. So my dear, that's not longitudinal. That's okay. Now, if I draw a line like this, what will you call that one?
Horizontal.
Horizontal. So the horizontal is okay, yeah. Longitudinal line can be both vertical, or we can say, okay, a longitudinal wave can be both just okay, vertical and or horizontal. Okay, peace be with that, my dear. But what we say is, okay, where are we? Okay, good. Oops, 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 oops. So that's okay. What we may be talking or what we may be referring to now is that our saying is that sound waves are longitudinal waves. Did you get that? Clear? Okay. So let's just say it's okay. What the do we mean by it's okay being a longitudinal wave? Now let's just get back to our okay as where we were or where we started today. We say it's okay, we have a source, right? Is that clear?
Yep.
Okay. Now this source is okay, that's going to is okay produce sound. So you can say it's okay, it's going to be okay, the source of sound. Okay. What did we need for this sound or as okay, or the sound waves to that are produced by this source as you travel? We will need a medium with particles. Did you guys get that?
Yes.
Okay, so let's just say that, okay, yes, here, the sound, well, okay, yes, comes out from here. Now, what we said was that, okay, yes, sound waves was mechanical waves, or yes, okay, a mechanical form of energy. And why did we say that? That was mainly because, yes, okay, for the sound wave to be able to travel, or for that energy to, yes, okay, be transmitted, if you want to put it that way. We will need, yes, okay, these particles here to move. Now, in our case, yes, okay, the movement of our particles is going to be as okay like this. That makes sense. So we can mainly say that, okay, this particle here is okay, that's going to move back and forth like this. So is this particle going to be moving back and forth like this? This particle is going to be moving back and forth like this. This is going to move back and forth like this, and so on. Did that make sense? Okay, we will come back to that thing is okay in just a little bit as well. But the thing that happened here is that, okay, yes, the sound wave actually is going to be okay, a longitudinal wave. Because in this case, yes, okay, the sound is going to be traveling in this direction. Did that make sense? So what causes, yes, okay, something to be, yes, okay, considered a longitudinal wave, where we can say that, okay, yes, the wave travels in the same direction as the motion of the particles. Did you guys get that?
Yes.
Or we can say it's okay that they go in the same direction. So right now, it's okay, practically it's okay as I'm speaking. I'm the source. What I do is when I talk, particles in air mean yes, okay, starts moving back and forth like this. And that's why it's okay, the sound travels like this. Did you guys get that? Yeah, okay. Now you can say it's okay, a particle will travel like this and come back, will travel like this and come back. But it's going to be it's okay along this plane here. And that's the direction in which it's okay. In either of these direction is going to be it's okay through which it's okay the sound will travel. So because you can say it's okay, the direction of the particle motion and the direction in which the wave travels are the same. That's why you will call it a longitudinal wave. So that's why it's okay, sound wave is a longitudinal wave. Did that make sense? Okay. Now, although not written, well, that's okay. Just you guys want to, that's okay. And another form of wave, which is going to be a pressure wave. Have any of you ever heard that's okay, a big boom? And what is it that you may feel?
A vibration.
Or a pressure, right? So that's going to again be as okay, a pressure wave. So pressure waves are also longitudinal waves. And pressure is just okay as another form of energy. Okay. Any questions? Clear? Okay. Now, for instance, yes, okay, if I lay down on the floor, or it's okay, or tilt my head back and start, yes, okay, talking or laughing or snoring or whatever I end up doing, right, okay? Or okay, as in terms of physics. In terms of physics, yes, okay, the sound will be traveling like that. Okay, clear. Why? Because okay, sound wave is or was or will remain longitudinal waves. What's the criteria for being a longitudinal wave? That okay, the direction of the motion, a particle motion, and the direction in which the wave travels is the same. Did that make sense? Okay. Now, dear guys, another example or another type of wave is going to be as okay, what we call transverse waves. Now, please, 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 although, yes, okay, it is discussed in this chapter here, but please keep in mind, guys, yes, okay, your sound waves are not transverse waves. Okay? Sound wave is not transverse wave. But I think, okay, the reason that's okay that they talk about it here is that's just okay, tell you that, okay, there is another form of wave which is called transverse waves. Okay. And what is it that you is okay? What's going to be is okay the major difference between is okay being a longitudinal wave versus a transverse wave? Now let's just look at that. So we can say it's okay. There may be it's okay, let's say it's okay, a source of wave. Or we can say it's okay, a source of the wave. Here, for instance. But this is going to be as okay, a transverse wave. Yeah, okay. Now, guys, if you just remember from your medical terminology, you will remember, yes, okay, what the word transverse would mean. Yes, guys.
Through.
Through or across, right?
Yep.
That's just for simplicity's sake, say yes, okay, across. Okay, so what will be an example of a transverse wave? We will mainly say it's okay, let's just say it's okay that even here it's okay, the particles may be moving like this. But the wave will be traveling like this. All this. Or rather, yes, okay, let's just do it the other way around. That probably should be easier. That we actually may say it, okay, yes. Let's do this one. That the particles move like this. but the wave, which is going to be a so-called transverse wave, that was like this. If that makes sense. So where we mainly can say is okay that, okay, yes, where the direction of the wave travel is transverse or across the direction of the particle motion. So I think it's going to be it's okay transverse if it's going to be across or form or may look like a cross. Yeah, this was okay, yes, your particle motion, for instance. And this was the direction in which the wave would be traveling. Okay, but please, 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 guys, keep in mind, your sound wave is not a transverse wave. Okay, your sound wave is not a transverse wave. So what could be examples of, okay, it's a transverse wave? Although you're probably not going to be asked about it. But that's okay if somebody wants to know, that's okay, things such as X-rays is a transverse wave. Light waves are transverse waves. Okay. So what is the difference between okay, transverse versus longitudinal waves? In longitudinal waves, yes, okay, the particles moves like this back and forth, right? This is also going to be the direction in which the sound wave is going to be traveling. But okay, we can say it's okay, the particles may move like this, but this would be the direction in which the wave will be traveling. So yes, okay, they make the motion of the wave versus the motion of the particles makes a cross or runs transverse to one another, right? Did that make sense? Or through? Clear? You come across, that's okay, a rail crossing on the street where the train tracks runs across the street, right? Okay, you have the street run like this. And okay, the train track coming like this. That's transverse. Clear? Or run across the street. Where you can say, it's okay, 2 lanes on a street or a highway are going to be, it's okay, longitudinal. They run in the same direction, right? Okay. Clear? Okay. So that becomes just okay longitudinal. So longitudinal along, transverse across. And things that run across one another is going to form a cross. Did you guys get that? Okay, but the takeaway line here, guys, is that sound wave is longitudinal waves. What does it mean to be a longitudinal wave? That the sound is going to be moving in the same direction as the particle motion. Now it's okay, although it's okay, the particle moves like this, back and forth, for instance, as we may call it. Okay. But the sound is going to, yes, okay, in this case, that's okay, be traveling this way. Now, if some of you are saying, let's say it's okay that we are sitting in a room, some of you are talking, you will be producing a sound. Those particles are still going to move like this, but that sound will be traveling towards me if I was facing you, right? Okay, and I'll be able to hear the words that were coming out of your mouth. Did that make any sense? Okay, so that's what makes it longitudinal. Okay, had it been the other way around, well, okay, yes, then we're having transverse. That the particles may move like this, but the wave moves like this, or vice versa. Okay, then that would have been considered to be a transverse wave. No, sorry. Sound is not a transverse wave. Sound is a longitudinal wave. So what have we learned so far? What have we learned so far? First was, that's okay, sound is a form of energy. Clear? Okay. Okay. What we briefly touched, we're going to just, okay, talk more in detail about that. Sorry. In later chapters, is that, okay, yes, one characteristic of most form of energies is that, okay, yes, that they can change their form. Okay. A pretty visible example is, okay, yes, here. This light here in the background. Clear? Okay. Now this light here may be on. I even have lights on here. Okay. Now to begin with, yes, okay, what was it? Electricity. That electricity will come from other forms of energy. We can, okay. Okay, but let's just talk it that way. Okay. Now what is that this light is going to cause? Okay, it's okay. Electricity hits the bulb. It produces light. Okay. But have you ever wondered that, okay, yes, if you walk into a room which is, okay, yes, super well lit, 1,000 of light bulbs, but okay, it's not going to be as okay, only as okay, not only is it going to be as okay, super bright in that room, or as okay, well lit up. But sooner or later, what is that you also will feel?
Heat from it.
Heat. So what is that we can say now that, okay, yes, the electricity or the electrical energy that hits the bulb doesn't only produce light, but also produces
Heat.
huh?
Heat.
Heat, exactly. Clear? Okay. So your stove. Now, I don't know what kind of stove you have. You may have a gas stove. That's fine. Okay, gas that's going to be okay using combustion energy, but it's going to produce heat. But it's okay. You may turn off all the lights in your house, pull down the curtains, and you'll see it's okay. That flame not only produces heat that's going to just okay cook your meal, but will also produce light. Which are just two different forms of energy. Okay. So yes, okay. Energy, yes, okay, will be able to, yes, okay, change their form. Okay. So our sound energy, well, okay, to begin with, was not sound. It started off as electrical energy. It's going to be, yes, okay, the job of the source. Or let's say, yes, okay, for ultrasound, it's okay, your transducer to transduce or convert that electrical energy into sound energy. Otherwise, you might have been, yes, okay, electrocuting the patient. And I don't think that's what he or she had signed up for. That's okay, I showed up in the clinic to get electrocuted. Okay. If somebody wants to get that, yes, okay, there can other means of getting that done. Okay, I think I just okay. Okay, guys. Should we just take a short break? Okay. So yes, okay, just refill your coffees or whatever. And let's say that I see you guys back at 10:40. Yep. God, it's okay. Yes, I hadn't. So all is okay. Your compression and refraction has not been recorded. You can just look at it. Okay. So what do we say? Source. This will be the direction in which the sound wave will travel because of the back and forth, back and forth, back and forth motion of the particles. And that's why we call sound waves longitudinal waves. Right, okay. Now, what does it mean for, yes, okay, sound waves? Yes, okay, what do we call, yes, okay, when particles in the medium are brought closer together, we call that being compressed. Whereas, okay, as when particles are at a greater distance from one another, or stretched apart or kept apart, that's what we'll call being rarefied. But what you actually will see is that, okay, particles which at one stage might be compressed get rarefied. Particles which were rarefied get compressed. So this means, okay, just, oh, yes, okay, the cyclical changes is going to, yes, okay, go on and on and on and on, as long as you can say, yes, okay, the source produces sound that travels through the medium in which the particles are, yes, okay, compressed, 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 or rarefied, 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 rarefied. Did you guys get that?
Yep.
Good. So during a practical demonstration, yes, okay, get compressed. I get close to it, okay. So that you can see. And mainly, yes, okay, due to, yes, okay, this motion of the particles was needed. Because yes, okay, otherwise, yes, okay, the wave would not travel. Why? Because, yes, okay, the particles would not get close enough to one another to cause the transfer of energy. Clear? Okay. So what we actually, yes, okay, will say that, okay, yes, right here, yes, okay, the transfer of energy is going to be max between A and B, C and D, E and F, and G and H, because they are the ones which are compressed. Where, okay, yes, if we talk about the amount of energy transfer between B and C, D and E, F and G is lowest because they are the particles which are rarefied, or it's okay, farther away from one another. Okay. But then it just becomes just okay, like those, have you seen just okay, those rally races? Where a team has 4 members and they run a distance. They have that toilet paper roll or whatever you want, or roll of anything, or as okay, that they made as okay, transfer over to the next member, and then he or she starts running on to the next one and pass it on. Clear? Okay. So you can say, okay, they get close to one another before it's okay, that torch or roll of paper, what the blue it is that they pass on to the next team member, can be passed over. Okay, if the distance between them is okay as 200 meters, okay, then okay, they can't transfer it or pass it over unless they throw it. But that would be cheating. That would be cheating because okay, the rule is that you have to just okay run up to that next team member before you can pass the pass that object, whatever that is. Okay, guys. And that's why I say it's okay for the first few topics of this chapter is okay, I may be jumping a little bit back and forth. Oh, yes, okay, right? Right? Sorry, guys, I have been jumping a little bit around. Back and forth, just like okay as a particle motion. Okay. What would be another word for yes, okay? What would be another way of saying yes, okay, back and forth?
Side to side. Left to right.
No, because my dear, that would be like this. That jump from right to left or left to right. It's not side by side or side to side. This will be back and forth, right? So can back and forth be yes, okay, expressed using yes, okay, another phrase that will mean back to forth. Or back and forth.
Maybe oscillate.
Well, that's more of a technical term, my dear.
Would it just be front to back? No.
Okay. Yeah, that could be it, but that's not the one that I'm looking for. Yes, hit. You guys never heard of something called to and fro? Yes, Teresa has heard about her because her name starts with T.
Yeah, but I haven't heard that phrase in like a long time.
Yes, exactly. So maybe it is obsolete because they not use it anymore. But that's another way of saying it's okay back and forth, to and fro. Okay, guys. So that's okay. Good. Now, yes, guys, just go on to page um, page 11. So we'll jump back to page 11 from page 12. Okay. And this is probably okay, the last frog jump between the first 3 pages for now. Okay. And what is it that you see at the bottom of the page, guys? You see a yellow box, right?
Yes.
Which is divided into 2, right?
Yes.
Good. And you see 2 things. One is going to be as okay, what we will call an acoustic propagation. Oops, properties. You may also see as okay what I refer to are called the biologic effect. Okay. Now, guys, what is going to be as okay common factors for both acoustic propagation properties and or biologic effects? The 2 common factors that we'll be dealing with here is going to be as okay, we can say as okay, the sound and medium. Is that clear? So the 2 main things that we will see is okay, if we talk about is okay, acoustic propagation properties and or biologic effects is going to be as okay, it's mainly going to be as okay relation between as okay sound and medium. Now, guys, and I know this from experience, but let's see if we can break the record. I got 7 lovely students in my group now, right? Okay, I had bigger groups, smaller groups, but at some random point where I asked this question here, what is an acoustic propagation property? People tell me yes, okay, or yes, okay, give me an answer which explains what a biologic effect is, and vice versa. So you can say, yes, okay, this is the stroke volume and cardiac output of ultrasound physics, or one of them at least. Right, okay. Clear. So let's see if I can break the record, because otherwise at some point it's okay, 50% of you guys may flip around with that. Yes. So let's see if we can break the record. Okay. Let's see if this group here is okay, can be the record breaker. Otherwise, yes, okay, we're going to go to and fro from, yes, okay, chapter coming ahead back to chapter 2. Okay. Okay, guys, let's see. Okay. But I'm not going to be asking you guys before I've talked about it. So what is an acoustic propagation property? Okay. And it may, you can say, okay, the thing that may, yes, okay, make it confusing is, okay, it's me, it's okay, there's going to be, yes, okay, relation between sound and medium in both of them. But let's see, yes, okay, maybe the colors will help us. So we can say, yes, okay, an acoustic propagation property. Now, before I go into, yes, okay, what the blue and acoustic propagation property, you may see, yes, okay, property is okay. Now, guys, okay, here the property doesn't mean that you say, well, this is my property, my house, my driveway, my backyard, my front yard, so on and so on. Not that kind of property. Okay, just properties of the sound, if you want to put it that way. Clear? Okay. Okay. Where the word acoustic. Does anybody know what acoustic mean? Well, it is just okay pertaining to. But acoustic pretty much okay, yes, okay, just as a fancy word that means sound. Or it's okay pertaining to sound. Is that clear?
Yes.
Good. Propagation. Now you may say it's okay, propaganda. But propagation is mainly it's okay. That's going to again, it's okay, be a fancy word for, because it's okay, progressing, or in this case, it's okay, as travel ahead or move on. Okay. So the word propagation is going to be, it's okay, a term that we'll come across again. It's okay in the next chapter as well. But just okay as a fancy word of okay, yes, that mainly is okay, just means to move on or travel ahead or whatever. Yep, okay. Now what is going to be, yes, okay, guys. So what's going to be your acoustic propagation property? We can mainly say, okay, that's going to be the effect of the medium on the sound. Or let me get more specific and say, yes, okay. Now we can say, it's okay, we may have a medium. Right, okay. Through which, yes, okay, of course, that's okay, this sound wave here is okay, will be traveling through it, through this medium here. Is that clear?
Yeah.
Okay. But what an acoustic propagation property is going to be is okay. Okay. How is it that the medium is going to, yes, okay, change this sound wave here, or change the sound wave? Or we can say, it's okay, affect the sound. Right. So in our next chapter, chapter 3, we actually, yes, okay, will talk about, yes, okay, some parameters which are going to be, yes, okay, or some parameters of the sound that are going to be affected wholly and solely as okay as that sound travels through the sound wave. So those will be as okay an example of what we can call acoustic propagation properties. Clear? Okay. And a common example of, yes, okay, acoustic propagation properties is going to be something that we'll talk in more detail about in chapter number 6, which we'll call attenuation. But let me just give you guys, okay, as not necessarily for ultrasound, but generally as okay. Because all this comes from, yes, okay, general day-to-day concepts. You may not think about them, how it happens, but there's physics in anything that happens. Yeah, okay. You turning on the stove, yes, okay, that electricity turning into heat. That's physics. That water coming to a boil, that's physics. And that boiling water actually is okay, boiling your egg. It's also physics. Did that make any sense? So let's say, yes, okay, example of physics. To explain, yes, okay, what would be, yes, okay, an acoustic propagation property, or more correctly, yes, okay, what would be an example of attenuation? Which is mean, yes, okay, going to be, yes, okay, due to the effect that the medium had upon the sound. Now let's say that, okay, yes, there's a big boom happening somewhere. The people standing right next to that area where that big explosion or whatever or sound was produced may hear that sound so loud that it almost is okay deafened them. Clear? Some people who are standing not that close, but still, yes, okay, close enough, may, yes, okay, still hear that sound, but not to that deafening intensity. But it's okay, you can mean says, okay, the more far and far and far and far and far away you okay, are standing from where that sound was produced. What's going to happen? You will not be able to hear the sound to be as loud. Why? Now you say, okay, that sound traveled through a medium. But why is it that, okay, as a person who was standing right there, hears just, okay, a sound that is almost deafening, loud, and somebody who may be standing, let's say, it's okay, or be at a distance of a mile, may just say, okay, there was something that happened, or not be able to just, okay, hear the sound as loud. Is because, okay, at a distance of a mile, or maybe 2 miles, or 5 miles, or whatsoever, that sound has attenuated. Which is mainly as okay due to as okay the effect of the medium through which the sound had traveled. So as far as okay as your audible sounds that we are able to hear are concerned, what will happen? It gets dimmer and dimmer and dimmer, right? Okay. Did you guys get that? So somebody will come and say, "Oh shit, that was loud," and someone will say, "Yes, we heard something. What the hell was it?" And someone will say, "Well, okay, what are you guys talking about? We didn't hear anything." Okay. Why? Because it's okay, they were standing, yes, okay, at a distance, it's okay, at which, yes, okay, the sound didn't reach with a high enough intensity to be audible to the normal human ear. Why? Because it travels, yes, okay, through greater, yes, okay, space through the medium, where it just becomes so weak that, okay, yes. So is that a blessing or is that a curse? Is that a blessing that you can't hear, yes, okay, every sound? Or is that
Yeah.
yeah, okay. Otherwise, you will go bananas, right? Okay. If you are able to hear, yes, okay, any sound produced anywhere by anybody, yes, okay, that was going to get, okay, too much. Clear? So that's a cosmic propagation property. So what caused what caused the sound, yes, okay, get dimmer, 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 is an example of a cosmic propagation property. But what causes that? That means, okay, that's going to be the medium that will affect the sound. That makes sense. Clear? Okay. In ultrasound, what was going to be our medium?
The tissues.
Tissues. Okay. So the sound wave that we transmit into the body of the patient probably are not going to travel through and through the patient. Why? Because, okay, first of all, as okay, sound energy, or at least as okay, the sound energy that we use is not so high that it will be able to just, okay, penetrate or travel all through the full thickness of the patient. Clear? And mainly it's okay because of the medium as well. Now, guys, when we go on to yes, okay, or another factor, or which we as okay call biologic effect. Now, guys, biologic effect is okay. May also be known as bioeffects. Yeah, okay. But what's going to be as okay the bioeffect? There is going to be as okay the effect of the sound on the media. Did you guys get that?
Yep.
Clear? So have you guys heard of what is known as a tit for tat? You can roughly say, yes, okay, that's what's happening here. A tit for tat. Okay? Because, okay, the medium may affect the sound as the sound travels through that medium. That was what we call an acoustic propagation property. Did you guys get that? The other way around, that sound that travels through the medium may also affect the medium. And that's what we'll call a biologic effect or bioeffect. Okay. Now the mechanism behind this is again going to be briefly talked about in chapter number 6. And detailed accounts of this, what you call bioeffect or biologic effects is going to be discussed in chapter 24. Okay. But what did I stay at today's class? Or what did I start to say in today's class? What were my first words before good morning and all that? Well, after good morning and all that, sorry.
You asked if we had any questions.
Okay, all that comes under all that.
Is that when you said we were gonna jump around the chapter?
Okay. Just to give you guys a warning. Not warning, but it's okay, because you may get lost. Where you might get all this from. Okay, when I start talking about sound waves, what was the first thing I said about sound waves? Or sound?
Form of energy.
Form of energy. Good. And what did I say about energy as well?
It changes form.
It changes its form. Exactly. Clear? So that's what's going to happen here. Okay. Which will become where we lead to a biologic effect. Or what we also can call a bioeffect. The air sound travels through the medium. Okay. Now, the effect that the sound has upon the medium is going to be what we call a biologic effect. But how? Pretty much because, what will happen that some of the sound energy that you produce that travels through the medium is going to be absorbed by the medium. Clear? Now, it was sound energy, okay, that is going to be absorbed by the medium. But that doesn't mean that now your tissues are singing Christmas carols or the national anthem or whatsoever. Clear? Okay. That sound energy is going to be converted into another form of energy, which will be heat energy. And it's going to be that heat energy that then will affect the tissues, which we call biologic effect, or as we will talk about in the last chapter of this book here, it will be bioeffects. So it was the sound that affected the tissues. But the mechanism behind it is that, some of the sound wave that travels through a medium is going to be absorbed by the medium. So it's not going to be all of it that makes its way through. Okay. Or you can say this way, maybe let's put it this way. that the sound wave may pay a little bit of tool through the medium to let it go through, right? You guys know what tool is? If you're out for a long travel, yes, okay, you may be crossing a lot of bridges. And what is it that you'll be playing?
Oh,
Exactly. And what is that going to do to your bank account?
drain it.
Drain it. Okay. Now, my dear, there's something known as an easy pass. You know that, fellow? Yeah. So you can reduce the drainage by that thing. But yes, okay. Right. Okay. So, okay. But okay, as what is that? We can say it's okay. The tissues may, yes, okay, use that tool too. Okay, so okay, this is some energy that I got from it's okay, the passing cars or it's okay, people passing through. I'm going to, it's okay, put that money in a fireplace and warm myself up. Okay. So yes, okay, when we said earlier, yes, okay, after saying that, okay, a sound was a form of energy. But okay, if that energy is being, yes, okay, absorbed by the tissues, that energy will change its form from sound energy and become heat energy. Just like, okay, yes, the dude here is okay in the background. He or she produces light. But it's okay, some of that light will also be converted into heat. So that was your acoustic propagation properties versus bioeffect or biologic effects. So it was a tit for tat. The medium affects the sound and the sound affects the medium. Did you guys get that? Okay. So the sound that the medium has upon the sound is what we call an acoustic propagation property. The effect that the sound has upon the medium is what we call a biologic effect or bioeffect. Any words of wisdom? Anybody want to say something? Anybody wants to ask a question? So what was sound? Form of energy. Clear? Okay. So we can say, okay, what do we call that form of energy? That sound is going to be sound energy. Okay. How does sound travel? It travels in forms of waves. What do we call those waves? Longitudinal waves. Why do we call them the longitudinal waves? Well, okay, because what we need for sound waves to travel is a medium which has particles. Those particles get into motion. That makes them mechanical waves and a mechanical form of energy. that the motion of those particles and the direction in which the sound wave travels is the same. So that's why we call them, what we call sound wave, a longitudinal wave. Right. Okay. Now, as far as as the particle motion was concerned, yes, it could be back and forth or to and fro. Longitudinal to the direction of the particle, or yes, movement of the wave. Okay. What did we call the phase? Yes, when the particles were close to one another, was compression. Whereas when they were far away from one another would be rarefaction. But that's going to be that rhythmic oscillation of compression, rarefaction between neighboring particles. Clear? Okay. Now, what we need for a sound were mainly two things: a source and a medium, generally speaking. Okay. Later on, we will talk about the source as your ultrasound system. And or your transducer. Whereas the medium is going to be your tissues. Yeah. Okay. Now, sound traveling through the medium will be affected by the medium, and that's what we call an acoustic propagation property. As that sound travels through the medium, that medium is going to have its own effect upon the sound wave, which can be labeled together as what we will call an acoustic propagation property. An example of that is going to be attenuation. That's attenuation is mainly that big boom that you might not have been able to hear if you were standing at a distance of maybe a mile or a couple of miles away from where that big or smaller explosion happened. The other way around is effect of the sound wave upon the medium. Clear? Okay. Now that's there would be a reason that's why you might not hear be able to hear that big boom at a distance of certain miles. Mainly because in the way where there are buildings, different structures which absorb some of that energy from that big boom. Yes. Okay. So what may happen to buildings which are close to a big boom, broken windows, things like that. Okay. That was the summary of what we have gone over through so far. Still any questions? Okay. Anything that was funny? No? Okay. So yes, bioeffect and acoustic propagation property, or AP as I may call it, Now, AP is not an official abbreviation for acoustic propagation property, right? Okay. But if you look at it, it's okay, it's APP, which is AP. Okay. But it's okay, it's a tit for tat. Okay, so what's a tit and what is a tat? Well, okay, yes. I don't know what the hell a tat is, but anyway. Or chit for chat or hit for hat or whatever. Okay. Okay. Well, it's okay if there's that's okay. If the sound affects the medium will also affect the sound. Okay. Okay, guys. Okay. Let's take your lunch break, and when we come back, we will talk about, yes, okay. I'll briefly touch on, yes, okay, what we'll call acoustic variables. And we may just briefly mention, yes, okay, what we will call, yes, okay, the acoustic parameters. Okay, so would it be fair that I see you guys back at 12:45? Is that fair enough?
Yep.
Okay, guys. Have fun till then.
I have a question.
Yes, my dear.
It was just like a syllabus question. I was just looking at it and there's quiz 3, it says it's in August. So I just
Okay.
just wanted to let you know so you could fix it when you fix the
Okay. It's probably not August. Yes. Let me fix that. It's probably just okay. Let me just do that right now. Let's see. Can I have a testimony question? That's unless you guys want to.
take it in August.
Yes.
Hope we're long past that. I hope we are scanning by August.
You're better than you have more to. Okay, let's. Good. That should be correct. Uh, yes. Now let me check my paperwork stuff. Okay.
Yeah, it's good. I just looked.
Okay, guys. Any questions? Good. So let's talk about, yes, okay, verb recall. Acoustic variables. Okay. Now, please, guys, okay, as I said earlier, acoustic is just a fancy word for sound. Okay. Not necessarily on ultrasound, but any sound. Yes, okay, sounds that you may be able to hear. So pretty much, okay, as every sound is going to have us, okay, what we'll call variables. Yeah, okay. And what we actually can say is that, okay, yes, a sound is identified by, and we're just going to just, okay, use a term that Kristen used earlier, oscillation in, okay, we can call it, okay, or acoustic variables. Clear? Okay. What did we mean by oscillation? Well, okay, because it's okay, mainly it's okay, varying distance. Anything is okay that varies. And most likely it's okay in sounds, just okay, this is going to be it's okay, rhythmic oscillations. Okay. So please, guys, this sentence here is written in your book. Please highlight that. Okay. Clear? Now the question just is, okay, yes, what three factors or parameters or whatsoever can we call acoustic parameters? There's going to be one which will be pressure. There's going to be, yes, okay, another one which will be density. And the third one is going to be, well, that's okay, your book made, yes, okay, just say, yes, okay, mention a distance. But which practically, yes, okay, is going to be, yes, okay, we can say it's going to be the distance of particle motion. Did you guys get that?
Yep.
So guys, please, 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 point number one is, okay, that you should know is, okay, what your three acoustic variables are. Yep, okay. So what were all three acoustic variables? Pressure, density, and distance. Or more correctly said, distance of your particle motion. Is that clear?
Yep.
Good. So we can mainly say it's okay, every sound is going to, it's okay, be made up of these three variables here. But if any of these, that's okay, changes or oscillates, we will have sound. Now we come to, yes, okay, the little interesting thing, because, okay, we're going to be talking about each of these here individually. We will talk of their units, and we will start talking about relationships. Right? So before I get started with relationships, is there anybody who still is confused about what it means to be directly proportional? Okay. Anybody who has the least star of what it means to be inversely proportional. So you guys are fine about that. 100? Okay, let's see. Okay, guys. Good. So first acoustic variable is pressure. Now pressure, guys, is going to be, and this means, okay, just the bookish definition of it. It's going to be, okay, the concentration of force per area. Is that clear?
Yep.
Yep.
Good. Now, even if you look at the word pressure just in regular English, I hope that's the language that I'm talking to you guys in, right? Good. Okay. Earlier this morning, when I asked if anybody had any issue with us moving the date of the quiz at the end, somebody said something, and I said, well, the remaining of you were pretty much okay, quiet. So what did I say? No pressure. Clear. Okay. Let's say it's okay that the 6 out of you guys had it's okay, made it or not. I say, well, okay, be good. We have no problems. And one of you say, and now I put a force, not necessarily it's okay, a physical force, okay, on that person or in that area. That will be a pressure. So that's why I say it's okay, there's no pressure. I'm not going to put any pressure on any of you. If you can't, then you can't. If you can, okay, yes, well and good. Clear? Okay. So pressure is just going to be, yes, okay, where you can say it's okay. The amount of force that may be put on a certain area. Now, area is just going to be, as okay, a unit of distance. But please keep in mind here, it's okay, when we say unit of distance, that unit had to be, a unit of distance has to be, for it to be called area. What do we need to do for the unit of distance?
It has to be squared.
It has to be squared. Did that make sense? Okay. So what pressure main is going to is, okay, account for is the amount of force applied onto a certain area. Okay. Now, this fellow here is okay, can be expressed by 2 units. So we can say it's okay. No, let's do it this way. The unit of pressure can be just okay what we call a Pascal. But what we also can do is, okay, yes, we can make a unit of pressure pretty much just okay from the definition. So generally speaking, yes, okay, the basic unit of force is going to be a Newton. Named after Isaac. An area, well, okay, we talked about, yes, okay, that unit of area that already. It could be pretty much okay as just any unit of distance squared. You can say meters squared. You can say it's millimeters squared. You can say whatsoever. As long as it is any unit of distance being squared, it's a unit of area. Did you guys get that?
Yep.
Yeah.
Good. Any questions? So either yes, okay, a Pascal or a Newton per meter square will be the unit for what we call pressure. Yeah, okay. So how will we do? Yes, okay. How is it that we may calculate a pressure, for instance? Which is going to say, it's okay, well, okay, what is going to be the force applied over a certain area? That's going to be the pressure. But for that, we may need two things to be able to calculate the pressure, right? Right? We may need a force, which can be as okay, X, Y, Z amounts of newtons. Okay, we may then need an area, which is going to be as okay a certain unit or a certain number. Okay, by as okay expressed by the unit of meter square. Yeah, okay. That is what's going to give us, that's how it's okay. Or again, so numerically, it's okay, what we may need to calculate the amount of pressure that may be applied onto a certain area. Okay, guys. Now the art of relationology. So guys, your pressure and force they are going to be as okay what we'll call directly proportional. What did that mean? What did we mean by that? That for instance, okay, no, sorry. That if the force is increased, then pressure is increased. Whereas, okay, as if force is decreased, then pressure is decreased. Did you guys get that?
Yeah.
Okay. Now, some of you may say, yes, okay, but what about the area? Where is the area in this? Because the area also plays a role in determining the force or pressure here, right? Okay. But what we mainly just says, okay, want to establish is, okay, what is the, we can say, okay, direct relationship between pressure and force. What is the direct relationship between pressure and force? they will be directly proportional. And what we do is, okay, mainly is, okay, to establish the relationship between these two, we say, well, okay, we're not going to be playing around with the area. The area remains constant. Clear? Okay, because if we start changing on with the area as well, well, okay, that's going to have its own effect upon the pressure. Clear? Okay, so just to establish that, okay, what is the relationship between pressure and force? To establish that, that's when we say, okay, if you increase the force, how is that going to affect the pressure? If you decrease the force, how is that going to affect the pressure? For that, yes, okay, we keep the area constant. What does it mean to remain constant? It doesn't change. Did you guys get that? Clear? So what we mainly saw was that when pressure or when force is increased, pressure increases. When force is decreased, pressure is decreased. So that's how we mainly can establish that, okay, pressure and force are directly related to one another. Then we can mainly say, okay, the third factor here is kept constant. Now we can take an example. Or let's say it's okay that we take two examples. We say, okay, we want to calculate the pressure. And let's say it's okay, we want to calculate the pressure. Okay, now mathematically, it's okay, what was the formula of pressure? It was okay as force by area. Yep, okay. Now, what we already have said, yes, okay, that in both instances, okay, we are going to keep the area constant. So we can take any area and say, okay, this is the area of, let's say, it's okay, a circle. Let's say it's okay that this circle here is 2 square meters. Did you guys get that? So 2 square meters. That's your area. Whereas, okay, yes, on one circle here, well, okay, this is going to, on one area is okay, that's going to be, it's okay, a greater force and a lesser force. To begin with, it's okay, let's just say it's okay that we apply a greater force. Let's say that we apply a force of, let's say it's okay, 10 newtons. Applied on, okay, as an area of 2 square meters. Our question is, okay, yes, okay, that we will actually, yes, okay, now, yes, okay, based on, yes, okay, this relationship here is okay, we should get a great pressure. Okay. But we can say, okay, let's calculate what the pressure becomes. Now, 10 divided by 2, I hope everybody will be able to, yes, okay, agree upon that is going to be 5. Yep. Okay. Now, what is that all going to be? But that will mainly mean that we have, okay, yes, a pressure, which is, okay, where are we? Okay. 5 newtons per meter square. That was your pressure here. There, okay, yes, in this other instance here, is okay. We says, okay, let's just, okay, go over the lower force. So let's say it's okay that we apply is okay a force of 6 newtons onto the same area. Now what's going to be your pressure then? Well, I hope everybody will be agreeing with me that, okay, yes, 6 divided by 2 equals 3. So we'll have as, okay, a total force of, or pressure of 3 newtons per meter square. Where you can see here that, okay, yes, where we applied a weaker force on a same area, we had, okay, yes, a lower pressure. Whereas, okay, as where we applied, okay, as a greater force of 10 newtons onto the same area, we ended up with, okay, as a greater pressure. Which then, yes, okay, just established the fact that I said that pressure is directly proportional to force. Did you guys get that? So what's the relationship between pressure and force? They are directly proportional. Okay, how do we establish that? Yes, okay. And that's how they do it. It's not something that I just made up. That's how, yes, okay, physics will work. Because, okay, if I start changing, it's okay, the area at the same time as I change the force, well, okay, the area is going to have its own effect upon the pressure. Okay. So what are we going to do to establish the effect? Or let's say, all right, let's put it this way. I establish the relationship between pressure and area. You're going to do the very same that we just did, but in this case, yes, okay, we'll keep the force constant. So that's how we'll be able to determine, okay, what's the relationship between the pressure and the area. Clear? Okay. But is everybody clear about this one?
Yeah.
Yes.
Good question. So let's just go to our next one and see. Well, okay, what we now need to establish is, okay, yes, what is the relationship between, or we can say, okay, pressure and area. Now, what they are going to be is that they're going to be inversely proportional. Okay. Did you guys get that?
Yes.
Okay. Now, sorry guys, but this sign here, what this sign here is okay, just marks or symbolizes is proportional. Now, if I wrote this sign here, it's okay, alone and alone, that's going to be as okay directly proportional. When I write this sign here, it's okay like this, followed by yes, okay, something like this, and okay, there's going to be written something here. This becomes just okay, inversely proportional. So what I mean, yes, okay, just said or wrote is that okay, yes, your pressure is inversely proportional to area. Now, practically, yes, okay, what would that mean? That mainly mean that okay, yes, if the area is increased, the pressure will decrease. Or if the area decreases, the pressure will increase. So this is the direct relationship between area with pressure. And of course, that's okay to establish that. That's okay. What do we need? That's okay. Force is kept constant. Yeah, because we just saw that, okay, yes, the force actually is okay, was directly proportional. So if you keep on changing both of them, well, okay, they're each of them going to have, yes, okay, their own effect upon the pressure. Did you guys get that?
Yep.
Right, okay. Because the force is going to increase the pressure, the area is going to decrease the pressure. Okay. But just to establish that, okay, where is the direct relationship, or how is it that area is wholly and solely as okay related to pressure? To establish that as okay, we don't mess around with this fellow here. So the same thing, guys. Now we can mainly say as okay, the force that we may be applying onto two areas, we just keep that the same. We can say as okay, 10 newtons. Did you guys get that?
Yep.
Right, okay. Whereas, okay, yes, in one case, as okay, we may have, let's say, it's okay, a big area. Let's say it's okay, we have a big area. Let's say 10 meters squares. Whereas, okay, in the other cases, okay, we may have a smaller area. 2 meters squares. So what do we have here? Is okay, we have a greater area. And what do we have here? It's okay, we have a lesser area. But our question is still going to be the same as okay, where is going to be the pressure in both cases? So how do we calculate our pressure? That's okay, it was mainly it's okay, just the force yes, divided by the area. And now you just put the numbers in. So we had 10 newtons. 10 newtons in areas of respectively 10 meters squares and 2 meter squares. And now you just do the math. Now 10 divided by 10 is 1. So here's okay, our pressure is that's okay. You have a pressure of 1 Newton per meter square. Whereas okay, we just do the same over here. It's okay. 10 divided by 2 is 5. So what do we have here? Is okay, we have a pressure of 5 newtons per meter square. So yes, okay, I hope everybody will agree to that. Okay, yes. Here. Let's put it this way. It's okay. We have a lower pressure because of a greater area. Whereas here we have, okay, it's a greater pressure, mainly it's okay because of so let's do this. We have a greater pressure. Mainly it's okay due to a lower area. Yeah, which means okay, just establish that pressure is inversely proportional to area. Did that make sense? Okay. So if you got this much, now what can we say as okay here in our equation? That force was the numerator and area was the denominator, right? Okay, force was the numerator, area was the denominator. So whatever you are going to be calculating is always, whenever you have okay equations like this, will always be directly proportional to the numerator and inversely proportional to the denominator. Just put it this way. You had 20 cookies. A group of people, yes, okay, show up at your door, singing Christmas carols. Now it's Christmas carols. A month ago it was okay as candies and okay as Superman and Batman and okay as witches and whatever nuts. Right? Whichever season you want to talk about, I don't mind. So if there was a less number of people out there, you say 5 people, each person will get 4 cookies. Whereas it all of a sudden, yes, okay, it was a group of 10 that showed up. Okay, yes, you only had 20 cookies. You can only give 2 cookies to each of them. So in this case, I can say that's okay, the numbers of cookies that each person is going to be getting is going to be inversely proportional to the number of people showing up at the door. The more people that show up at the door, yes, okay, less number of cookies is it that each of them will get. Clear? Okay. Because, okay, there are this many people, I have this many cookies, okay, yes. Whichever way you want to check it. So mathematically, yes, okay, or we can say it's okay. Well, you will see being done again and again and again and again and again and again and again. Where you have a factor, where you have a parameter, where you have a variable, that is determined by two factors where one is going to be a numerator and one is going to be a denominator. That factor, that parameter, that variable is always going to be directly proportional to the numerator and inversely proportional to the denominator. That is simplifying as, okay, the relationshipology subject. Or as, okay, what we just saw, what we are going to see in just a minute, and what you will be seeing at different points of this course here is, okay, I just summarized it. It's not really physics, it's plain math. Here I just, okay, use the numbers so you guys can see that I'm not just bullshitting. Okay. Any questions about pressure? Any questions about, yes, okay, the relationship between pressure and force? Or the relationship between pressure and area?
I have a question.
Just go ahead, Maria.
Could you then say that force and area are also inversely proportional if
No,
pressure is the same?
no. They will not be inversely proportional. What it means to be inversely proportional is that if one increases, the other one will decrease.
So would force and area ever be seen together like that or no?
Maybe for something like if you want to calculate something else, but not here.
So for our purposes, we don't need to know a relationship between those two? Between
But-
area and force?
No, because they are not going to be related.
Okay, so they're unrelated.
Yes, at least for now.
Okay.
Okay. You can only say as, okay, that would have been related. If you say as, okay, if you say then pressure, or let's say it's, okay, force, determined by as, okay, pressure over area or something like that, or multiplied, okay, but don't go into as, okay, all that. Okay, you can actually say that, okay, yes, pressure multiplied by area. That's right. Yes, pressure multiplied by area will be equal to the force, or vice versa. Okay. But that's a little bit too complicated for now. Okay. So the main thing for now that you guys would not for now, it's okay, pretty much okay forever. At least we talk as okay, at least as long as we talk as okay, ultrasound is what is the relationship between pressure and area? Not sorry, pressure and area and pressure and force. So they were directly related. Okay, pressure and force was directly related. Pressure and area was inversely related. Yeah. Okay. How and why? Okay. But those relationship was established when you can say, okay, that the third factor in the equation was kept constant. So when we established the relationship between pressure and force, we kept area constant. Because we saw that the area was going to have its own effect upon the pressure. Okay, so to establish that, okay, as what we may call as direct relationship that pressure and force add together, we kept area constant. Likewise, when we want to establish as the relationship between pressure and area, that's when we kept the force constant. And as we could now say, change the area and say, how that affects the pressure. Did that make sense? So that establishes the relationship between area and pressure. Okay, but if you change both pressure and area, well, the pressure is going to just if you change both, let's say it's force and area, the force is going to just cause that is going to just a change of force is going to be directly related to the pressure, whereas the area is going to be inversely related to the pressure. Did that make sense? Which mainly mean the more the force increases, well, the more is it that pressure will increase, or vice versa. Right? Whereas, yes, the more the area increases, the more is it that the force will decrease, or pressure will decrease, and vice versa. Because pressure and area were inversely related. Did that make any sense? Okay, but the simple cheat to remember all this is that, yes, in the equation of how we calculate the pressure, force was the numerator, which makes it directly proportional. Area was the denominator. Did you guys get that? Okay. Now, my dear, if you just go on to the next fellow. And he or she is going to be as what we'll call density. Now again, yes, guys, you will see the density is again going to be as a concentration of. So again, yes, that's going to be as a compare, yes, mean, yes, we can say it's usually when we talk about concentration of, that's always going to be as two factors. That is will determine or play a role in the density. And again, you can again see as that one is going to be as a numerator. And there is going to be another one that's going to be a denominator. Okay, but the numerator and denominators that we have here that makes up what we will call density are relatively going to be mass. Okay, what people commonly as may mistake as weight. Versus volume. Now, guys, that's when we talk about as the unit of density. It's pretty much as just going to be as the unit of mass, which could be as kilogram, milligram, gram, whatsoever, per unit of volume. Okay, now usually that's you will just keep that as a liter. Or you can go as per gallon, it doesn't really matter. Okay, But okay, if you want, just okay, keep the units within the same system. So that's why we go and say it's okay, kilograms per liter. That's going to be as okay your unit of density. Or the unit of volume could also is okay because that's okay measured in a unit of distance cubed. So meter square, centimeter square, mile square, whatsoever. Or cubed, sorry. Did that make sense?
Yep.
Now, have any of you seen the movie Titanic? Okay. Now let me just ask a question. Why the hell did Titanic sink?
Because it took on too much water after it hit an iceberg.
So what did the water do?
It filled up the ship
Well, let me ask you this. Why didn't Titanic sink before she was filled up with water?
because there was no hole in the boat.
Okay, good. Why did Titanic get a hole? Because it hit an iceberg, right? Okay, why did she hit an iceberg? Because the guys who were standing in the watchtower were too busy looking at Rose and Jack, right? That's probably not how it happened. But anyways, now, but you may say, okay, how is it that, okay, that big ship didn't manage to sink until she was filled with water? It may sound strange, but it's okay, the density of a ship actually is okay, is less than density of water. That's how it's okay, it's still able to float. Okay, so it's not just a matter of okay, us making okay a triangular or a square or something. Well, okay, the triangular thing is that's okay for a reason, but I'm not going to go into all that. But anyways, okay, okay, the bottom of the ships are like this are not flat. Okay, good. Okay, guys, so let's look at this thing here. So you can already see it's okay where I'm going, right? So that's the units of, yes, okay, your two components that, okay, as mathematically makes up. That's okay, or you may need to, yes, okay, calculate your density. So what can we say of what we already know? Is that, okay, density. He or she is going to be, as okay, directly proportional to mass. Oops, shit. And if I'm not mistaken, that density is going to be, as okay, inversely proportional to volume.
And I ask a question. So is the numerator always going to be directly proportional?
Y-
And the denominator is always going to be inversely?
Yes, my dear. I think that's what I said a couple of times.
Oh, sorry.
Now that's fine. You might have missed it. Okay. When you go, yes, okay, with equations like these. And that's why I say, yes, okay, this is me, that's okay, that's the bottom line of, okay, it's understanding the art or the subject of relationshipology. Right, okay. When you have, okay, and it's not only as okay related to as okay all the general math, which they may as okay just implicated into physics. Clear? Okay. But what is the must to establish that okay, yes, density and mass are directly related or directly proportional? You keep the volume constant. Right? Just as we did with area when, yes, okay, we established the relationship between pressure and force. Yeah, so likewise, okay, in density, how will you establish the relationship between the density and volume? You keep the mass constant.
Can you show the screen again? I wanted to write down the relationship.
No problem, my dear. Where were we? Here we go.
Thank you.
No problem. You able to read it, dear? You may be able to figure it out.
Yeah, so density is directly proportional to mass, and density is inversely proportional to volume,
Exactly.
right?
Exactly. And what would that mean? That would mean that, okay, yes, if we increase the mass increases, the density will increase. Clear? Okay. Whereas, okay, yes, if the mass decreases, the density will decrease, or vice versa. Whereas, okay, as on the other hand, we can say as okay, if volume decreases, then the density will increase. Whereas if we say that volume increases, then density will decrease. Now, guys, what I said the other day when we talked about is okay, mass, for instance. You know, this should be something that we use to just okay express, or a term that we use for solids. Whereas okay, volume is mainly as okay used for liquids and gases. So yes, okay, you can say it's okay, measure the quantity. Yeah, okay. So yes, okay, this is your relationships. Now we can still, yes, okay, go on, yes, okay, say, well, okay, density, we says, okay, is directly proportional to mass. But in this case, yes, okay, we may keep, yes, okay, volume is kept constant. Determine that. Yeah, which means that okay, yes, greater mass will be greater density. lesser mass will be lesser density if volume is constant. So we can say, so, okay, we may have, okay, as a volume of something. Let's say it's, okay, 3 liters. 3 liters. Now, 3 liters, yes, okay, we may add, or we may pour a solid substance. Yes, okay, yes. All kgs of sugar. Whereas in the other, we may, yes, okay, just put 6 kgs or 6 kilograms of sugar. Now, don't do this experiment in your kitchen. I'm not going to be paying for your sugar. But okay, as in both instances, okay, we'll just end up, okay, as with, we can say, okay, different density of sugar solutions. There you may, yes, okay, just do the math and say, well, okay, here we have 12 by 3. Whereas here we say, it's okay, we have 6 by 3. But we can say, yes, okay, we're sure to say that, okay, so what we had here was agreed mass. Here we had a low mass. But now we just do the math. 12 divided by 3 is 4. So yes, okay, our density is going to become okay, 4 kilograms per liter. Whereas if we do our math down here and we say it's okay, 3 or 6 divided by 3 is 2. So what do we have here? We have a density of 2 kilograms per liter. Where I hope everybody will agree that, okay, yes, 4 is a greater number than 2. But why did we end up, okay, having a high density here and a low density here? Because here we added a greater mass in the same volume. Here we put a lesser mass in the same volume. Did that make sense?
Yeah.
So if we just do the exact same thing here, but now it's okay with our mass constant. That's okay, mass kept the same. Let's say it's okay, we keep it 12 kgs in both cases. But it's okay, in one case we'll say it's okay, we add it into 6 liters. Whereas here we may add it into, it's okay, 24 liters. Maybe says, okay, here we have a lower volume. Whereas here we have, okay, it's a greater volume. Just to establish, okay, what the relationship between the density and volume will be. Now you just put the numbers in the equation that we know is the masses per the volumes. And do the math.
Is the top one supposed to be 6, not 12?
Oh, sorry, yeah. That's fine. Okay, 6. So 12 divided by 6 is 2. So your density in this case is, okay, becomes 2 kgs per liter. Whereas, okay, yes. Okay, good. Whereas, okay, in the other case, 12 divided by 24 is 0.5. So that's actually going to be, okay, 0.5 or half, right? Okay. So here is, okay, our density is going to be, sorry, half a kg per liter. But you can mainly say, okay, where we had a low volume, we end up with a greater density. Where, okay, is where we have a greater volume, we end up with a lower density. Hence established that, okay, density is inversely proportional to volume, which was the denominator of your equation of how to calculate density. Yes, guys. But if you got this much, okay, as at least you can say is okay, we are heading in the right direction. Okay. So that's going to be as okay, not just for this course, anywhere you go is okay. If something is calculated by as okay, by dividing a numerator by a denominator, that thing that you calculate is always going to be directly proportional to the numerator or inversely proportional to the denominator. And you can take it in any way you want. Number of cookies per people, number of peoples per cookies, what and what not. Yeah. But you have to just, okay, remember the formula. Right? So here it's okay, it's not mass over area, it's mass over volume. Clear? Okay. In pressure, it was force over area, not force over volume, not force over mass or something like that. That's pretty much okay, fixed. That's the only thing about physics that you can't play around with. Formulas. Okay. Pressure over force over area, kind of force over is okay. Volume can be something else. At least we can say it's okay, it's not pressure. It can be something else. What the is that going to be? I don't know. So it's okay. If I don't know it, you don't need to know that. Unless you want to go on and do a PhD in physics and become Newton or the next Einstein. Clear? Okay, guys. So let's talk tomorrow. Yes, okay. I start off with okay. Distance, there's not much to talk about, but anyways, good. View, yes, okay. Start where we finished. Okay. Any last words of wisdom?
Nope.
Okay, guys, then I guess I will see you guys tomorrow at 9:00 a.m. Now enjoy the day, stay warm, and well, okay, take care.
Bye.
All right, see you tomorrow.
Okay,
Tomorrow.
take care, buddy.